Okay, welcome everybody. We are going to talk about a couple different things today, basically wrapping up Chapter 2. So hopefully you've been reading Chapter 2 in the process of completing Homework 2, and we'll just kind of finish that up today. And I want to start today by talking about multi-channel sound and how SuperCollider deals with multi-channel signals. So, a great majority of unit generators are monophonic, with the exception of the UGens that are, specifically meant for panning and spreading into multi-channel signals. But sine, osc, white noise, etc. These are all monophonic by default. So if you just give them basic parameters and play it, you'll get a monophonic signal. And I have the server booted already, and we'll just open up the meters. And so if you run s.meter, you'll get a little display of the input channels and output channels that are associated with your sound card or audio interface. And so right now I've got one mic plugged in to the device that I'm using for input, so you can see my voice there. And then if we were making any sound, you'd see it on channels 0 and 1. So we'll just make a little pink noise. And well, let's we're not gonna. This is just muscle memory here. I just instantly add the exclamation point to. So we're just going to play pink noise, and it just comes out of the left speaker, and you can see that that's consistent with what we see on the meters. Inside the context of a unit generator function, would somebody go and close the door just while we're here? Appreciate that. Just so we're not disturbed by hallway noise. When you've got a unit generator function, and the signal you are playing is an array of signals, SuperCollider will interpret that array as a multi-channel signal with the number of individual channels in that signal equal to the number of items in the array. So if we play the array pink noise, comma, pink noise, we now have two pink noise generators, and SuperCollider automatically assigns those channels to consecutive hardware output buses. And we could add another one like this. Nothing interesting will happen visually or audibly, and that's because by default SuperCollider only assigns two audio channels to hardware outputs. Maybe we'll come back to this a little bit later. It is possible to reconfigure SC Synth's view of your hardware channels. For example, if you're doing a quadraphonic or octaphonic piece or something like that, what you'd do is you'd configure the server to have that many channels associated with hardware outputs before you boot the server. And once you boot and then run s.meter, this will pop up with even more outputs and possibly inputs if you also want more than two microphones or input sources. So generally, I think there was a version of SuperCollider a while ago where the default was 8 hardware inputs and 8 hardware outputs. And maybe this was just deemed a little too confusing for new users, and so they changed it so it's 2 and 2, which is probably a little bit more realistic in terms of what most people are going to be working with. But the point I'm trying to make here is that if we provide an array of signals, they will automatically get assigned to consecutive channels, and boom, we have a multi-channel signal. So it's very convenient. And that is why, a moment ago, you saw me type exclamation point 2, because as we know, this is a syntax shortcut for creating an array of copies of the thing it applies to. So here we get a similar but not quite identical result. You can see we've got two pink noise generators, and the way the meters are moving, you can see they're perfectly identical. So being a shortcut for the dupe method, it quite literally means duplicating. It's going to take this generator and make an exact copy of it. So we copy this to both channels. So this is obviously much more convenient than having to explicitly type out individual pink noise generators to just duplicate them. But one of the nice and sort of magic features of multi-channel expansion, as it's called, is that if you provide an array of values for one of the arguments of a unit generator, like this, or even simpler, like this. So pink noise is you know, taking a look at its arguments and says, okay, my mul argument is the array 0.2, 0.2. And so this is where the expansion part of multi-channel expansion comes in, where what this becomes is an array of 2 unit generators, and the values in the array are distributed to the unit generators in the resulting array. So if I were to do something like, well, let's just play this first of all. And this is slightly different from what we just heard. You can see on the meters that these are 2 unique pink noise generators. And that's because we're not duplicating the generator itself, we're duplicating the argument. And then that argument, 0.2, is provided to 2 different pink noise generators, and so they become different. So this is a subtle difference. For deterministic generators, something like this, you know, it doesn't matter if we duplicate the argument or if we duplicate the ugen, because this is a fully deterministic ugen. So as long as you provide it with the same values, you'll get the same result. But pink noise is stochastic, so we'll get different results if we duplicate the generator versus the argument. It's a very subtle difference, but it is important to keep in mind. So if I were to do something, let's go back a few steps. And if we provide the array 0.2, let's do 0.3 and 0.04 and play this. The 0.3 is assigned to the first pink noise, 0.04 is assigned to the second, and so you'll see a greater signal level in the left speaker. And this works you know, the same way for you know, frequency arguments or what have you. So if we say 400 and 700, something like this, get 400 in the left, 700 in the right. And if we provide another array here, something like this, then again, the arguments get distributed to the unit generators. So we'll have one pulse wave with a frequency of 400 and a mul of 0.2, the other in the right channel with a frequency of 700 and a mul of 0.01. Yes, very obnoxious sound. But you get the idea. And let's do something a little bit more interesting to demonstrate that multi-channel expansion will propagate through a ugen function with multiple expressions. So let's do some white noise. If we just leave it like this, it'll be quite loud, but I'm going to pass it through a bandpass filter. And the frequencies will be, let's say, 1,000 and 3,500. BPF takes a third argument, which is the reciprocal of the quality of the filter. So as these values get very, very close to 0 on the positive side, the bandwidth gets narrower and narrower. So something like 0.001 would be a very high quality bandpass filter, and this is going to really filter out most of the spectrum, and so it's going to be fairly quiet. So I'm going to give it a fairly high mul value. And these are the arguments if we want to be extra clear. So this will sound like this. Turn that down just a little bit. Maybe this down. Right? So we have a center frequency of 1,000 in the left, 2,500 in the right. And then let's use a pulse wave to modulate the amplitude. So we'll do 6 hertz and 9 hertz with a width of 0.1. So 0.5 would be a perfect square wave with equal up, equal down. 0.1 is going to favor the down, so we're going to get sort of a short on and then a longer off per cycle. And so that's going to sound like this. So 9 pulses per second in the right, 6 pulses per second in the left. And if we were to just do something like this, right? No, we're not going to do any array here. It's a lot like this more simple mathematical expression. I mean, I'm just using the same numbers. It's not quite the same thing, but the 6 gets applied to both numbers. And so in this case, we have this 2-channel signal with a different frequency, and then both would get pulsed by 6 hertz. So if we get just a single value, not an array, it'll just apply to every value in the array. And if we provide an array, then the left channel will stay with the left, the right channel with the right, and so on. And I suppose there are a lot more what-ifs that might arise from this kind of logic. And for the most part, I've found that the behavior of multi-channel expansion is pretty intuitive. The main thing to watch out for is that you can send a 100-channel signal to hardware outputs, and it will go ahead and write that signal to the lowest 100 audio channels, but you're only going to hear the first 2 under default conditions, because the other ones are just simply not connected to any hardware devices or your sound card. So let me talk now about a couple of unit generators that are specifically designed to deal with multi-channel signals. So let's go back to a monophonic signal here. So right, just in the left, pan 2 is a unit generator which expects a monophonic signal at its input. So that would be sig. Kind of the same thing we're doing with this filter. The first thing we provide is the signal to be processed. Same with pan 2. And then a pan position. -1 means left, +1 means right, 0 means equal power panning in the center. So we can put a 0 here, and then play this. And you can see we've panned that mono signal in stereo. And I'll swap this out for mouse X. And the horizontal position of the mouse will control the pan position. And of course, you can use whatever you like here, a LFO or any sort of thing like that. One of the absolute biggest mistakes I see, not just in this class, but people who are post comments on my videos and things like that. Just something I see in code all over the place is this sort of thing. We exclaim 2 on an argument, which transforms this single pink noise into an array of 2 pink noises, each with an amplitude of 0.3. And then that 2-channel signal is passed into pan 2, which is expecting a 1-channel signal. Not an array of signals, but just a single UGen. And let's just run this and see what happens. So I'll move the mouse. You can hear there's like a little bit of amplitude fluctuation, but it's not working correctly. It's not actually panning. You can see that on the meters, and you can hear it too. So I'm just going to do a little bit of pseudo code here. So we just say we have pink noise. That is sig right here. And when we pass it to pan 2, this is the input signal, and pan returns an array of these 2 signals and handles the level adjustment based on the value of the pan position. So what we actually get being sent to speakers is something like this: an array of arrays. Each one is a stereo signal. And so when we send this to our speakers, I might have this slightly wrong, but I think what the server does is it plays this signal on buses 0 and 1, right? And then it plays this signal also on buses 0s and 1s. So when we pan left, we hear this signal on both channels, pink noise, and when we pan to the right, we hear this signal on 0 and 1. And so I think it's something like this. I might have the actual details somewhat incorrect, but the point is it doesn't work correctly. And the point additionally is that you should always be mindful of the channel size of your signals when you are passing them to unit generators that might expect a certain channel size. So if you are going to pan, you need to be giving it a monophonic signal. But then the question is, okay, let's say I have a 2-channel signal, a stereo signal, and then I want to actually just, I want to do the same sort of panning thing. I want to pan hard left and only hear the left channel, and I want to be able to pan right and only hear the right channel. You can't do that with pan 2, but there's a different class, balance 2, which is the same concept, but it expects to receive 2 input signals, a left and a right. And both of these individually are expected to be monophonic signals. And so how can we do that with the understanding that what have I done? Okay. Well, what I'm trying to show is that this is SIG, an array of 2 UGens. So how can we provide a left and a right from SIG? What do we do syntactically?
We could index the stereo array.
Right.
I'm surprised it doesn't just, I'm surprised you can't just give it an array and index automatically.
I mean, sure, it would be cool if you could just do like this, and it says, okay, I'm expecting a stereo signal, and it's going to automatically split them up. But this UGen is designed to take two separate inputs as 2 separate arguments. So it would be SIG at 0 and SIG at 1. And just for clarity, let's make this something like that in the left and this in the right. And so now we have a 80 hertz pulse wave and pink noise in the left and the right, and then we're just indexing into that array to temporarily split these signals into 2 mono channels, and then balance 2 resynthesizes them, adjusting the levels of these 2 signals based on the pan position. And you can see on the meters they are in the left and the right. So pan 2, balance 2 for panning a mono and stereo signal, respectively. And let's take a look at Splay, which is one of my favorites. This is a really nice UGen. It expects to receive as its input an array of signals of arbitrary size. It could be 2, could be 100. And it will output a stereo signal with each of the individual signals from the input signal positioned or panned linearly across the stereo field. So the first item is hard left, the last item is hard right, and the ones in the middle are distributed evenly. So there's some really fun and interesting things you can do with this. Let's do, we're going to do a lot of sine waves. Let's do from 80 to 80,000. Maybe not quite so high, and make 64 of these. So this is going to give us an array of just lots and lots of values, big sine cluster here. And there's probably a mathematically correct value here, but I'm just going to do 1 over 64. Just scale the amplitude of each one down by a factor of 64, since there's 64 nominal oscillators. And if we play this as is, well, we just hear the first 2 tones. This is a 64-channel signal, but it's just going to play the 0th one here, the first here, and the other 62 on silent, invisible channels. So, Splay to the rescue. This is all you really need to do. There's a spread argument. 1 is a full spread, and closer to 0 will collapse it to the center. There's a level. This is just another mul parameter for adjusting the overall amplitude. And you can read the help file if you want to see what else is going on. And I think Splay does some automatic level compensation by default, and so this 1 over 64 is probably going to be too much because splay is also going to be compensating for the based on the channel size. But so we can just simply dial that back to whatever we like. We can make 128 channels, and it really doesn't have any problem with just generating hundreds of oscillators on the fly, as long as they're not, I guess, too computationally expensive. But sine waves are easy. They're just table oscillators, and looking up values in a table is one of the simplest things for computers to do. We could also then go ahead and say, let's say sig equals sig times LF noise 2. And what we're going to do here is just do a kind of random amplitude modulation thing. So LF noise 2 is a low frequency noise generator, and the 2 tells us that is the version of LF noise which does quadratic interpolation between successive values. So it's going to pick 2 values per second, random values between, by default, -1 and +1, and quadratically interpolate between them. I think it's quadratic. Yeah, quadratic. And then we just want to give this an appropriate range from, let's say, 0.1 to 1. We're already scaling these down quite a bit, so this will give us kind of even more of a fluctuating character to the sound. Oh, too many. Okay, well, this is a good moment to, if you ever get this message, exceeded number of interconnect buffers. What we need to do here is say s.options.num wire buffs. This is a setting which determines how many internal connections are allowed inside of a UGen function, and 64 is, I guess, a little conservative. So let's just bring this up. And now, in order for this change to take effect, we have to reboot the server, which means I'm going to have to mess around with my audio routing to make sure I'm not losing the signal. So let me just do that real quick. Over here, where is it? Yeah, so we'll play this now, and it should work. Yeah. And good, we have signal. Okay. And you can see, it's not. This doesn't cost nothing. Down here in the bottom, the peak CPU is somewhere around 6 or 7%. So, but you can hear that each individual sine. Maybe you can't hear it, but you can imagine and understand that each individual sine wave has a sort of unique random amplitude modulator going on. So this is kind of on the more complex side of things that you can do with multi-channel expansion, taking advantage of the fact that the multi-channelness propagates through successive expressions. Yes?
So the LF noise wouldn't create 128 just by multiplying it by the sig, unless we explicitly define that there are 128 LF noise 2 U-channels.
So that's a good question. Just to walk through the channel count of this thing. So on the first line here, we create a sine osc, and for its frequency, the value is an array of 128 random numbers. So this becomes an array of 128 sine oscs. So sig here is an array of 128 unit generators, and we're multiplying it by an array of 128 noise generators. And so the behavior when we have an array and then some binary operation and another array, the default behavior is to apply this operation to corresponding items. So this would be 8 and 15. So that's what's going on here. The first sine osc in the 128 array of oscillators is multiplied by the first LF noise 2, and then the second by the second, the third by the third. Yeah.
But like LF noise 2, if we had just given it an argument of 2
yeah.
frequency, it would then be only one LF noise 2. It doesn't say, hey, I'm multiplying by, and as you know, with our math, when we multiply a single integer by an array, it's like it would all look at the value of that single LF noise 2 and then do the multiplication,
right,
rather than making a bunch to do that.
Well, I think it does end up Well, I'm not actually sure. Okay, so there's kind of two questions here. One is sort of what happens mathematically, and the answer is it's the same as this. It's like we have an array times a single thing, a number or a single UGen, and that operation applies to every sign-off here. Does it actually create 128 of these? It might. It might need to in order to actually build the result. So I.
So would that be then functionally identical to 2 dupe 128?
Like if well, let's take a look. If we just do this versus this, no, this is definitely more computationally expensive. So
Yeah.
so this so I'm probably wrong in that it actually does something more efficient if you don't explicitly multiply an array by another big array. If it's just a single UGen, then it is equivalent to doing this. You know, if you were to just duplicate, you know, the result is going to be the same, right? Where the whole cluster follows the same amplitude modulation, right? But this is I think just as inefficient. I didn't really look at the CPU there. Yeah. So this is just as taxing as this, but this gets you more interesting results because we're getting 128 unique generators. Good question. Yeah. Okay. I think that's sort of all I wanted to talk about with multi-channel expansion. It's a unique feature. I don't think there's really another audio programming language that has something exactly like this in terms of how simple it is to just have like a one line of code that produces this really rich, you know, multi-channel sound that can pretty easily be mixed down to stereo with Splay. So it's good to get comfortable with it. You'll see it a lot. And I'll just conclude this part of the lecture by just reminding you that you should always be mindful of, you know, because when you see SIG just like this, you can't tell by looking at it, is this a one-channel signal? Is it two channels? You really have to read your own code and sort of follow your own steps and just be aware. Okay, another big topic of chapter 2 is synth and SynthDef. So when we play functions like this, if we look in the post window, let's get rid of this. You can see that what is returned is something called a synth. We haven't actually explicitly made a synth, but when we have a function with unit generators and we play it, there's actually a lot of things that happen behind the scenes very secretly and conveniently to make our lives easier. And generally speaking, what happens behind the scenes is that the language passes the information to the language actually, I think, you know, sort of builds a SynthDef, sends it to the server, and then creates a synth based on that SynthDef. It also adds a bunch of stuff. It adds an envelope, which is what allows us to use .release on one of these playing functions. It automatically adds an output unit generator, which specifies explicitly the signal to be sent to a particular audio bus. So for the way I like to describe it is that when you're just doing quick testing and you just want to sort of check something or quick demo, function.play is very convenient and recommended. But when you are working on a project or a composition and you're imagining sort of many different variations on the same sound, you don't want to be making function.play function for every single one. You don't want to be copying and pasting. You can sort of make a function and then play it multiple times and get some reuse out of it that way. But the right thing to do is to actually build a SynthDef and then create a synth and just sort of do what SuperCollider is doing automatically for us yourself. So building a SynthDef is what it is it's a recipe essentially for some signal calculating or signal generating or signal processing algorithm. So a SynthDef can be something which just plays an oscillator, plays a noise generator, plays a bunch of oscillators with going through a bunch of filters. It could play back an audio sample stored in memory. Some SynthDefs don't actually generate any signal, but they expect to receive signal from upstream, and others will write samples to memory. So it's very arbitrary. And let's see, I kind of want to make something slightly interesting here. do a low pass filter. Actually, let's make an LFO here. This will be a slow triangle wave that goes from, let's say, 300 to 3,000, not 30,000. And I'm not going to bother with any panning here. Let's make a tremolo effect. Okay, fun little sound. We've done it with function.play. Let's walk through the process of converting this UGen function into its SynthDef. There's really only 3 major steps to doing so. So the SynthDef needs 2 things. It needs a name. And that's the first thing we provide, usually as a symbol. I think it can also be a string. So that's thing number 1. And then the next thing a SynthDef needs is just the UGen function. So we're just going to copy it and paste it right there. So the first thing, I said there are 3 things we need to do. The first is to pick a name and give that to the SynthDef, because if we're going to be making synths, we need to say, use this SynthDef, use that SynthDef. It's got to have a name, otherwise we have no way to refer to it. Thing number 2 is we have to explicitly tell this SynthDef what its output should be if it's supposed to have one. It will not do the usual thing of just outputting automatically the last line. We need to explicitly say, this is your output signal, and we do that with an output unit generator. Now, there's a couple of different output unit generators. Let me just quickly look at some of them here, or just show you where the category is. In, out, and so there's, let's see, so many. This in, this out, etc. Local in, local out, offset out, out, replace out, shared out. A lot of these I never use, but some of them are probably quite handy for various things. But I have always, for many years, have found that out is very general purpose and works in almost every case. Rare situations when you might need to use a different one. Out needs 2 things. It needs a bus and the actual signal. So I'm just going to put a 0 here and sig. Sig is the thing we want to output, and we want to send it to bus 0. And on our meters here, right here at the bottom, you can see the output meters are indexed 0 and 1. So this 0 means this 0. So it's going to send sig to this bus. And because sig is 2 channels, when this signal is written to bus 0, the additional channels in that multi-channel signal will automatically be assigned to consecutively increasing bus indices. So it's a 2-channel signal destined for bus 0, so it'll end up on 0 and 1. You do not want to do something like this, thinking you're being very clever and being very specific. But what's going to happen here, I think, is another instance of multi-channel expansion, where it will write the 2-channel signal to bus 0, placing it on 0 and 1, and also bus 1, placing it on buses 1 and 2. And so channel 1 will get this double dose where it's actually playing both signals in the multi-channel signal. So don't do this. The output bus should always be an integer, just to give you the lowest index bus. And then the last thing we need to do is add the SynthDef. That's the third thing, is just putting .add at the end of the SynthDef. Obviously, we need a name. If you forget output when you generate the synth, you just won't hear anything because there is no output. And if you forget .add, then you haven't actually sent it to the audio server, and the server will say this doesn't exist. In fact, let's go ahead and do that. Right? Let's pretend we forgot to do this stuff. It's not going to give you any error messages. It's going to say, okay, yeah, that's a SynthDef. There's nothing wrong with it, that I can tell. So then, if we try to make a synth, it says, I'm sorry, I don't know what you're talking about. And that's because we didn't add it. Now, if we add the SynthDef, now we run this again, what is posted in the post window is exactly the same, but now we won't get that. It says, yep, here's your synth. And in fact, if we look at the node tree, there it is. It's running, it's consuming CPU cycles, it's alive, but we haven't told it to output anything. So it's doing all the calculation, it's just not actually writing the result to bus 0. So if we then do the final third step here, run this, now we're back in business. And if we say x equals pulse demo, x.release, this does not work because what happens normally with function.play, if we, let's go back and do this one, right? Let's call this x. Now we'll release that. Yeah, see, lovely fade out. Because when we function.play, one of several conveniences that's automatically applied for us is the application of a gated amplitude envelope on whatever the last line returns. And that envelope automatically has a gate argument and a fade time. And so when we do .release, what actually happens is it's a set message that says gate 0 and fade time, whatever the fade time happens to be. So if we can do this, we can say x.set gate 0, fade time, very fast. My syntax is, it's supposed to be a comma. Right, there we go. So I'm just trying to highlight all of the very secretive things that happen behind the scenes with function.play, and it's supposed to be that way. It's a convenience, where we don't have to worry about a lot of the details that we usually want. But with the SynthDef, we have to do everything ourselves. So if we want to add an envelope, we've got to do it ourselves. So a nice refresher on envelopes here. We'll just make a default ADSR envelope. And the gate is going to be, do we all remember the various ways we can specify gate arguments? Right? You can do an arg declaration. Did I cover this last week? Okay. Right, so we can do it this way. We can do it with the pipes. Right? And we can also just build it right in as a symbol.rate sort of thing. And then there's one more thing we need to remember if this is going to be a terminal envelope here. And what's that?
Done action.
Right. If the end of this envelope means the end of the sound, we should specify a done action of 2 so that when the envelope finishes, the synth that it belongs to will automatically destroy itself. There's one more thing we're forgetting now. And if we just play this as is, it's not really gonna work the way we expect. Let's say gate 0. What's the problem here? It stopped, but it didn't fade out. Any ideas? It's another common mistake that I see. Yeah.
Did you apply the envelope?
Right, we've created it, but we haven't baked it into our algorithm. So it exists, it's part of the UGen function, and so when we set the gate to 0, it begins its fade out, whatever the default value is, and done action 2's itself, but it's not actually applied to the signal. Right? We've got to do this at some point. We've got to actually say, and here's how you're supposed to influence the rest of the signal chain. So now we'll get our sort of initial attack and decay. It sustains at its sustain level, and off it goes. Right? And we can check the node tree, and there's nothing there. Let's do it with the node tree just for extra clarity here. Right? There it is, gate 0. Away it goes. And that's really all there is to it in terms of SynthDef and SynthDef. We've got our function.play, which automatically makes a SynthDef, adds it, gives it in fact, it gives it a temporary name. Temp __ 58 is what this one got. But here we make our own name, give it an output, add it, and then we're free to make our synths. And then, so I'll ask you to turn some function.plays into SynthDefs and synths in the homework, but also I'll ask you to then add some arguments to give it flexibility, because that's really the strength here. So let's make trem hertz. Here's what I'm going to do. I'm going to say freq.kr80 plus the array 0, 1. Right? So whatever this value is, it's going to be itself, and then 1 greater than that. So we'll always have like a sort of 1 hertz binaural beating thing happening. And we can leave it there. You can use your imagination. We could also put arguments here for the frequency and range of the LFO. We could, put arguments here for the attack and decay and so on of the envelope. So if we do this, and then this, we can use a set message to change, for example, the tremolo rate. What we should definitely do is give ourselves an amplitude argument. Let's forget about that. Let's not scale the signal itself down by 0.10, and instead we'll just default this to 0.2. So now we have this. Right. And at any point we can say gate 0. Just going to fade it out. A couple of other notes on arguments. You might very, very likely want to start this synth with argument values that are different from the defaults. And if you want to do that, a synth call, after the SynthDef name, it accepts an array of arguments. And so we can say trim hertz :4, freak :200, amp :0.4. And the order doesn't really matter here. You can put them in any order you like. So this will sound like this. You can also chain multiple arguments in a single set message. And I'm pretty sure I talked about lag last week, where you can apply a lag to any of these arguments as well. So yeah, this is creating a synth with optional starting argument values, setting to new parameters while running, and then if you've given yourself the ability to do so, you can close the gate on an amplitude envelope, and that'll fade out. Making sense? Clear enough? Good. There's a small section in chapter 2 on alternate expression of frequency and amplitude. So if you've taken a recording class or if you have audio engineering experience, dealing with amplitude on a normalized scale between 0 to 1 is probably going to feel kind of awkward. If you want to just drop the sound by 6 decibels or 12 decibels, it's nice to be able to do that. There's a couple of methods. So AmpDB will take an amplitude value and give you the corresponding value in decibels full scale. So a value of 1 is 0 decibels. A value of 0 in amplitude is negative infinity, silent. And we can go the other way around. If we say, let's do negative 12 decibels, convert it to amp, that's going to give you the corresponding amp value. For frequency, CPS MIDI will take hertz and give you the corresponding note number. Middle C, MIDI CPS, that's going to give you the corresponding value in cycles per second. Very convenient. And there is also, I think this is in the chapter as well, but there's another pair of methods, MIDI ratio and ratio MIDI. This gives you, it converts between a semitone value, either positive or negative for going up and down, number of semitones, and the ratio by which a frequency must be scaled in order to transpose by that much. I'll give you an example. If we want to go up by 1 semitone, 1.MIDI ratio gives us the ratio in frequencies between C and C sharp. Or specifically from C sharp to C. So if we have 500 hertz, and I want the value in hertz, which is exactly 1 semitone above, I just multiply by this value, right? And -1, that's going to give us the reciprocal of that ratio. So this expression will give us the frequency for the value 1 semitone below. So this is 1, 12 is an octave. So this is always kind of funny. I don't know why it's not 2 exactly. It's very cute. Yeah, it's just, computers rounding errors, blah, blah, blah. So how would we look, in practice, this would be, we can say, give me the E flat above middle C, and we'll start this off at minus 12 decibels. It's really important to remember dB amp, because if you forget this and you specify negative 12 for a raw amplitude value, it's going to be 12 times bigger than nominal, and the polarity is going to flip. So very important to remember that. Right. Oh, I did MIDI ratio instead of MIDI CPS. Sorry. I was like, that's not E flat above middle C. Yeah, so MIDI ratio. What did we do there? This is the value that corresponds to the scalar value needed to transpose up 63 half steps. So we plug that in instead. So I sometimes mix these up. ECPS, right? And then we can set the frequency to be, 63 MIDI CPS. We'll keep that we'll just delete this for now. We can say times 3 MIDI ratio. Right, you can just sort of go up arbitrarily. And sort of awkward manual fade out. So those are useful, especially if you're trying to, imitate a melody or something like that. You just want to specify note numbers. Keep in mind that it's totally valid to use this on an array. You don't have to do it on every single number. Arrays understand this method as well, and we'll apply it to everything inside of them. And I think with just a little bit of time we have left, I want to talk about a couple of things with envelopes, just to kind of tie that off and just complete that unit a little more comprehensively. So let's simplify a little bit, and we're just going to get rid of some of these things. So I think that's fine. Just a quick side note here. You generally don't have to, like, once you add a SynthDef, you don't have to keep evaluating it every time you want to make a synth. You add the SynthDef once, it goes and lives on the server, and then you can call a synth from that SynthDef as many times as you like. But if you make changes to it, then you'll have to reevaluate it, and the old one gets overwritten. The one that was called Pulse Demo, this is now the new version. It just replaces the old one. Okay, so just making sure this sounds correct. Yeah, okay, that's fine. I'm going to replace this with env .new, which is just what we get if we don't specify anything. So env.new is the one I showed last time. It's got an array of levels, an array of times, an array of curves. Does this sound familiar? Okay. And I just want to show you a couple of fun things you can do with env.new. So so we'll go 0, 1, 0.1, 1, 0.1, 1, 0. For the times, we'll say 1 second to go from 0 to 1, and then a couple of short, and then 2 seconds to go down to 0. Just make sure I'm doing this right. So that's 6 things, and this one is 1, 2, 3, 4, 5, 6, 7, right? And then the curves, I'm just going to keep them linear for now. So I'm just going to set all the segments to be linear. And this looks like this. Okay, fun little envelope. And sounds like this. Okay, so the reason I'm bringing up env again is because there are 2 more arguments in env.new. The first is release node, and the second is loop node. So release node, and node in this case refers to an item in the levels array. We can think of the points between segments as the nodes on the envelope, little anchor points. So the release node it allows us to take a fixed duration envelope and specify a hold, the value at which the envelope will sustain when the gate is open. And without a release node in env.new, we don't get that. It just goes right through the envelope all the way to the end and never stops. So let's say we want it to sustain here. So this is 0, 1, 2, 3, 4, 5, release node 5. We're going to forget about loop node for a second. And now, as long as the gate remains positive, it'll go through and then hold at that last one, I think. Yeah, and there we are. And gate 0 says, OK, you're done. Complete the rest of your shape. So this is a way of turning env.new into a sort of custom ADSR style envelope where you can actually sustain it. Without a release node, then the gate basically has no effect. The gate will allow you to start the envelope, but then you have no control. It's just going to do its thing. Loop node specifies another node which then establishes a looping segment of the envelope. And so I'm going to specify 0 for this. And did I get rid of my plot? No, it's still there. Great. So this is our release node, and this is our loop node. And the behavior is this. The gate is open, the envelope begins, and as soon as it arrives at the release node, it immediately begins transitioning from this value to the node immediately after the loop node. So I think I've actually done this wrong. What I want is it to immediately go here. It's not what it's not going to do is teleport from this value to that value, because that would create a discontinuity and probably a click. And so env and envgen are very nicely designed to, when they're told to jump to a new node, they interpolate from their current value to the value that immediately follows the target node. So I think I'm actually going to specify 1 as the loop node. And so it's going to get here, and then it's going to take this much time to go from here to here, which is the node right after 1, node 1. And so now we're actually right, sort of looping in this middle section here. And then when the gate is 0, it will transition immediately from wherever it happens to be to the node immediately after the release node over this duration. So again, it won't instantaneously snap to a value of 1. We don't want that. We want it to go from wherever it happens to be down here. So if it's like somewhere in the middle, you can imagine it starting here or wherever it happens to be and then fading out like that. Yeah, let's do it again. Yeah. So this is really handy if you then want to do a sort of like an envelope that doesn't control amplitude but maybe frequency instead. And then you can set a release node and a loop node. And if you make the curve something much more extreme, let's see, can we plot this with the release and loop node? Then with a negative curve value, it starts to become almost like a step envelope. So there's a question on the upcoming homework where you're asked to do a little melody thing with an envelope, and this is a good general approach for doing that. And then one last thing. This is kind of touching on. I did a 0 exclam 6 here, and that gives us an array of 6 zeros, and so all 6 segments are 0. But if we just provide 0, it's the same behavior. That 0 is going to get paired with every segment. It's just going to automatically repeat itself as many times as necessary. So this will be 0 and 1. And then a good question is, what if we give it something like this, an array, but it's not long enough? Well, again, this array is just going to repeat itself as necessary. So the segments are going to alternate 0, linear, and then very exponential in one direction, I think. Yeah, linear, -10, linear, -10, linear, -10. And then if you look in the env help file, you can also do stuff like sine, and that will just sinusoidally interpolate between successive points. There's some other options there as well. So yeah, it's, as I said, you can spend a whole lecture, maybe more, on just unpacking the multitude of things you can do with env and envgen. Yes.
Can you use iteration to generate those arrays?
You can, yeah. I mean, this one's kind of custom, right? There's not really a distinctive pattern here, but what are you specifically imagining with iteration?
Well, like to just be able to say like 6.collect for the curve and have some sort of mathematical, thing in there. I guess this is not like useful.
Yeah. Let's say if we do like 1 over n or something. Oh, I guess that's going to be 1 over. We have to do n plus 1 because we can't divide by 0. Let's try that. Dot plot. Yeah. So the first value is going to be 1, and then 1/2. This isn't very interesting. We could just say n squared. Maybe that'll be more exciting. Yeah, so it starts out being 0, and then 1, and then 4, and then 9, right? Or yeah, just powers of just squares of the integers. So yeah, totally. I mean, the reason this works is because collect returns a new array based on and again, this is the 6.collect is the same thing as this, right? Just giving it an array of six of the first integer starting at 0. So yeah, it's just going to return a new array where each one of these values has been squared, and that's what gets plugged in for the curve. So yes, yeah.
Does the curve array have to be divisible by the number of nodes? Like if I have a curve array of size 5, does it just repeat the first element from that array and then?
If if the sizes of the typical thing to occur when doing env.new is for this array to have size n, and then these two arrays to have size n minus 1, because there's one fewer segment than there are points. But if you just give it arrays which are all different lengths, what I think will happen is the longest one determines. I'd have to do some tinkering. I've never actually really done this because it's kind of a weird thing to do. But I think the longest one will determine what the envelope will be, and then the shorter arrays will just repeat themselves, wrap back to the beginning and repeat their values as many times as necessary to provide all the necessary information to build the envelope. That's what I think will happen. But there might be some exciting and interesting results if you.
My obvious thought was thinking like there was an odd number of nodes, and if you do something where it's every other, so the array size is 2, it's not divisible. So I was wondering.
I think it'll just if you have like 5 nodes, and well, then you have 4 segments, so that's an even number. But if it'll just be 1, 2, 1, 2, 1, and then it's done because that's all it needed. So it won't complain. I think it'll just repeat the shorter array as many times as necessary, and truncating if necessary. Yeah. Okay, I don't want to keep anyone any later. I know we're sort of over time, as seems to be the case kind of often. So I'll once I have all the submissions, I haven't checked for homework 2, then I'll post the answers, and homework 3 is already up, and so that's going to be due in a week. I hope you have some fun. There's probably some fun things in there, some video game references and things. So enjoy, and yeah, thanks. See you next week.